So we'll finish this section with a couple more examples. So here we have a couple of systems of equations, and notice they're both homogeneous systems, right? The first system is homogeneous because all the constant terms are equal to 0. Same with the second, all the constant terms are equal to 0. So both of these systems are homogeneous, and that means they automatically have the trivial solution, where you just set every variable equal to 0. It'll automatically satisfy those systems. But what we're asked to do is determine if each of these homogeneous systems has non-trivial solutions. So in other words, is there anything else that would satisfy this system, for example, for part A? Is there any solution, is there any assignment of real numbers to x1, x2, and x3 that would satisfy each of these equations except the trivial solution where you set all three of the variables equal to 0? And to answer that question, we're actually going to go back to this theorem. And we're going to go back to actually the second statement in the theorem, which we didn't talk about too much up until now. We just went over it at the time, but we didn't use it yet. But here's where we're going to use it. The equivalents of A and B state that if you have a homogeneous system, now this is written in matrix form, but this is still a linear system. It corresponds to a linear system, and it has only the trivial solution exactly when A is invertible. So really what it's going to come down to is determining whether the coefficient matrices of these linear systems are invertible or not. So let's write the matrix equation for this first system, for part A. So this system is equivalent to AX equals 0, where we have the following, where A is the coefficient matrix. It's going to be 1, 2, and 3. Really, those are just the coefficients of the variables in the first equation, 1, 2, and 3. The second row will be the coefficients of the equation, or coefficients of the variables in the second equation. So you'll have 2, 5, and 3. And then the third equation will have coefficients 1, 0, and 8. So what do we know about this matrix? This is actually a matrix we just worked on in one of the earlier examples, right? We've already shown that that matrix is invertible in this example where we found its inverse. It just happens, it's a coincidence that this matrix showed up again, right? So we found the inverse, it's this. It does have an inverse. We don't care what the inverse is in our case now, we just care that it has an inverse. So since A is invertible, we can say that the system does not have any non-trivial solutions. Okay, so that's part A. And why does it not have any non-trivial solutions? Because remember, because A is invertible, the associated homogeneous system has only the trivial solution. That's what we're using here. Okay, and for part B, it's the same idea. We're just going to write down figure out what the coefficient matrix is here, and then we can check whether it's invertible or not. So this in part B, let's write it this way. How about we say this system has coefficient matrix, and let's write down the coefficient matrix, which is just going to be the matrix consisting of the coefficients of the variables in the left-hand sides of each of these equations. There's no reason we can't just call it A again. A is equal to, it's going to be a 3 by 3 matrix, so we've got 1, 6, 4, 2, 4, negative 1, negative 1, 2, and 5. And I'm going to say which is not invertible. How do I know that? Well, we did that one too, actually, in our previous example. We just did that one also. This was the example where we showed that this matrix was non-invertible, and we did it using the inversion algorithm. We got a row of zeros, and that's what told us that the matrix wasn't invertible. But the important part is that the matrix we had in that example is exactly the one we see now for the coefficient matrix. So that's why we know it's non-invertible. So therefore, let's say therefore the system has non-trivial solutions. Okay, and it's important to note that we didn't find them, right? We didn't actually find any of the non-trivial solutions for this example because the theorem doesn't tell you what they are. If you want to find those non-trivial solutions, you need to set up the augmented matrix for the system and start row reducing, and then but this tells you in advance that you're going to have a parameter if you do that. Okay, and you can check that as an exercise. Write down the augmented matrix of this system, row reduce it, and find the general solution, and you'll find out that you do need at least one parameter. That's what this tells you. Whereas in part A, you definitely won't get a parameter, because if you had a parameter, you'd have non-trivial solutions. But we've already confirmed using the fundamental theorem of invertible matrices that this system does not have a non-trivial solution. So you know if you solve this using an augmented matrix, you will not get a parameter. You solve this with an augmented matrix and you will get a parameter. Okay, so that's just a little bit of theory of elementary matrices and invertible matrices. We'll look at some more theory in the next section as well.